Welcome to this video on implementing a simple CNN for multi-class image classification. I am Laksit Nayak from Faculty of Applied Sciences, Rajarata University of Sri Lanka. My registration number is ICT 1819059. So, today we'll explore how a convolutional neural network or CNN can be used to classify images of fashion items into 10 categories using the Fashion-MNIST dataset. If you are passionate about machine learning or want to understand basics of CNN, this video is for you. Let's dive in. So, image classification is a fundamental task in computer vision where the goal is to assign images into predefined categories. For example, in this project, we classify fashion items like t-shirt, trousers, dresses, and sneakers. So CNNs are a powerful tool for this because they can automatically learn and extract visual features like edges, textures, and patterns from images. By applying CNNs, businesses like retail and e-commerce can automate tasks like inventory management and personalized product recommendations. So, here we use the Fashion-MNIST dataset, a popular benchmark for image classification. This data set you can see contain 70,000 grayscale images, each uh, 20 by into 20 by pixels, uh, 28 by 28 by pixel, categorized into 10 classes. Let me show you the class labels as follows. These are the 10 classes and associate class labels. Uh, Basically, here we are going to classify each fashion items into each of these. It's balanced, meaning each class has the same number of samples. This ensures fair performance evaluation without bias toward certain classes. So, uh, let's go to the training code. First, to prepare our dataset, we randomly selected 50% of original samples to create similar subsets. So basically, this Fashion-MNIST dataset is come as a CSV files for two separate files for training and testing purposes. So here, uh, for the uh, uh, for considering the efficiencies and resource availability, uh, we are trying to make the dataset as simple. So to prepare our dataset, we randomly selected 50% of the original samples to create smaller subsets. So here's how the data was split. So you can see uh, there are uh, 30,000 image for training and out of which uh, 6,000 were set aside for validation because 20 among the in between these training data set we get we will use 20% of it for the validation. So it means 30 in between this 30,000 of training dataset there are 6,000 training data for the validation, and we use 5,000 images for testing purposes. So uh, so uh, we normalize the pixel values to range uh, s- between 0 to 1 and use data augmentation techniques like rotation, zooming to enhance model generalization. You can see this is the data augmentation process. So here we extract our training validation and testing data. This is so here we use the suitable libraries and parts for the training, and So here we define the image dimensions and as 28 for uh, height and 28 for width. So basically, this because these images uh, are 28 by into 28 size of pixels. So we here we uh, get the batch size as 32. So this is the data augmentation and preprocess uh, preprocessing steps. So here we normalize the pixels between 0 and 1, and we use augmentation techniques like rotation, zooming. Uh, as you can see, this is the code for the relevant process, and we generate our validation dataset as follows. So you can see after successful running, it shows the 4,000 images as a training set belonging to 10 classes, and found 6,000 images belong to 10 classes. So that means this 6,000 means validation data set. So uh, so next we move on to the model architecture. So here, this is the CNN model that I used for this model training, and our CNN architecture is simple yet effective. So I'll explain each layer in this model. So it's starting in input layer. So you can see uh, it accepts 28 into 28 grayscale images. So as inputs, you can see here we use one channel for that, and we use um, yeah. So here uh, here we use convolutional layers and max pooling layers. So for the convolution layers, there are two layers with 32 and 64 filters to extract features like edges and patterns. So also these layers use actuation functions as a ReLU. And for the max pooling layers, there are two max pooling layers and these for the to reduce spatial dimensions, making computational efficient. And here we use one flattened layer. So it's basically converts a 2D feature maps into 1D vector. So uh, we use here dropout rate as a zero point 0.5 uh, for to prevent it from overfitting. And finally, we use fully connected layers. You can see these fully connected layers as dense layers. And here we use a dense layer with the first one is a dense layer with 128 neurons to capture high level features, and we use dropout layer to prevent overfitting, as I mentioned earlier. And finally, final output layer with 10 neurons and softmax activation to classify into 10 categories. You can see there. So for the compilation purpose, the Adam optimizer and categorical cross entropy loss were used to train the model, and compilation with accuracy as the our performance matrix. You can see this is the Adam optimizer as the as the optimizer for and this Adam optimizer for the adaptive this Adam optimizer has adaptive learning rate, uh, and it comes default as 0.001 as the default adaptive learning rate. And for the multi-class classification, we use categorical cross entropy for the loss, and we monitor accuracy during the training, and we put the matrix at accuracy. So this is the model architecture. You can see each layer and each parameters, you can see there are these mentioning total parameters and what are the trainable parameters. You can see there are 0 non-trainable parameters. So this is good. That means this architecture is a good effective architecture for CNN model. So then we move on to the training the model. So we train the model for uh, in first step. Uh, so actually we train the model for 30 epochs, and we use early stopping to avoid overfitting by halting training when validation loss stop improving. We also implemented model checkpoints to save the best version of the model. And so you can see we for the training purpose we train the model for entirely for 30 epochs. So first step we train the model for 20 epochs and see the uh, curves, how the curves behave when then we go for the another step. So here we use early stopping to avoid overfitting. It's a good technique, and you can see the patient's value as 5. This means uh, uh, it monitor the validation loss, and the validation loss stop improving when the validation loss is stop improving, and the model stop the training process, and use the train weight to the uh, this uh, model for here this train model 5, this Fashion-MNIST CNN model dot h5 for the saving of train models. Yeah, and to further uh, so, to further improve performance, data augmentation was applied, introducing variation in the images. So you can see in this here the model, the train model code, the model dot fit. We use train generator. That means in the training process, the this train generator. This means here you can see the train generator. Um, this train generator load the train images using data augmentation techniques within the our existing data directory. So uh, you can see this is the training process for the first 20 epochs, and uh, here uh, it stopped until at the 20th epoch. That means uh, we can this model didn't stop the training process uh, uh, because it didn't call the early stopping function. That means the validation loss didn't stop uh, didn't stop improving. So here we again so this is the uh, analysis graph for uh, the first 20 epoch. You can see the accuracy graph and the loss graph. You can see here the validation accuracy curves uh, and the training accuracy curves as here there you can see the training accuracy curves is under the validation accuracy. That means the validation accuracy curve performs well, and you can see the model loss curves, and you can see the validation loss curve is under the training loss curve. That means the loss is getting small. That means that this model uh, for the first 20 epochs it's trained perfectly, and we can uh, further train for another 10 epochs using existing uh, train model weights. And so first we train for it for 20 epochs, and second we train it for another 10 epochs. That means altogether 30 epochs we train the entire model. And finally we could able to reach the validation accuracy as 0.8783 as showing in the image. And after we plot the train history as below for the entire 30 epochs, you can see the validation accuracy curve is above the training accuracy. That means it performed well for the training process for the this train for the this training data set. And so let's we can move on to the model testing script. So here we can see that uh, a model testing script. So here we use the uh, our testing dataset directory for this testing purposes, and here we load our testing data and put some data augmentation techniques and load to the this test generator variable, and so here uh, we can see the classification report for the train model. So here we use the .h5 train model file and uh, load the train weights, and here we generate the classification report. So now let's evaluate our model on test data, and the model achieved here uh, we can see the model achieved accuracy of 90%, which is excellent for multi-class problem. And here's a summary of our classification report. So as I mentioned earlier, we can see the final accuracy, final test accuracy at 90% here. And here we can see high precision and recall for classes like trouser. So here, trouser, sandal, bag, and sneaker. So we can say the precision value and recall for the trouser class and the sandal class and the bag and sneaker class is much higher than others. And however, we can see shirt class struggle with a precision of 72 percentage and recall of 63 percentage. So here we can see the uh, uh, low precision and recall values for that. And this indicates overlapping features between shirt and similar categories like t-shirt and pullover. That's the reason. So here we can uh, see the confusion matrix for generated for our test data, and the confusion matrix provide deeper insights into misclassification for our uh, model. So actually the confusion matrix provide deeper insight into misclassifications. For example, you can see uh, most shirt misclassification were labeled as uh, t-shirt or top-ups, t-shirt or tops here. And similarly, you can see the coat instance were sometimes misclassified as uh, pullover or uh, dress, as the value mentioned as 37 and 21. And these errors suggest that visually similar categories can confuse the model, uh, which could be improved with more training data or better feature extraction. So this is the basically the confusion matrix. And actually this confusion within, you can see the within the confusion matrix the uh, actually the diagonal values, these diagonal values actually indicating the correct classification. You can see higher values for that. Yeah. Uh, and let's we move on to the our final evaluation, the the ROC curves and uh, AUC analysis. That means uh, we can show here the ROC means receiver operating characteristics curves, and AUC means area under the curve values. And so actually, uh, we also analyze these ROC curves for each class. The AUC values, that means the area under the curve values for most classes were, you can see, close to 1.0. You can see 0.991, 0.99, again 1, 1, 1. You can see uh, the AUC values for most classes were close to 1, reflecting excellent discrimination ability. So here key highlights include classes like uh, trouser, sandal, bag, sneaker had perfect AUC values of 1.0. You can see here, you can see the class number 6 as shirt. The shirt class has lower AUC of 0.96. That means consistent with its performance in the classification report. Uh, you can see the overall AUC values for each classes as here, and you can see the code which I use for this uh, uh, curve generation as here. And yeah, so finally, uh, so finally, let's visualize model predictions on a small sample. So uh, uh, here, here, this grid showing actual and predicted labels with confidence scores. You can see the uh, after the testing of some sample test images, the actual and predicted classes and confidence scores of each class for each image showing as in this grid. You can see uh, 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 as showing in this image. So you will notice that most predictions are correct. You can see uh, in first line actual is t-shirt, prediction is t-shirt likewise, and second row actual is trouser, predicted is trouser likewise, and you notice that most predictions are correct. But in case of misclassification, the model assign a high probability to visually similar categories which align with our evaluation matrix. So you can see here the third row, the first image, actual one is pullover, predicted one is shirt. The only here is the uh, only classification sample you can see because of these pullover and shirt categories showing similar visual uh, characters. That's the reason. And yeah, uh, to summarize, we successfully implemented CNN for fashion image classification, achieving 90% of accuracy. The model excelled in uh, identifying distinct categories like trouser, sneaker, but faced challenges with overlapping classes like shirt. Uh, Future improvements could include experimenting with deeper architectures, applying transfer learning, or using assembly methods for better accuracy. If so, if you like to explore the code, and uh, here's the you can find the GitHub repository in the description below. You can uh, find uh, after the video. Uh, so thank you for watching. If you found this video helpful, please give it a thumbs up, subscribe to the channel, and leave your question in the comment. Don't forget to check out the GitHub repository for the code and the YouTube link for a detailed walkthrough. Yeah, and thank you once again.